This is a quiz. This is a no talking quiz. This is a do it by yourself quiz. I'll get the clicker plugged in while you work on it. The quiz goes like this. We're going to solve f equals ma in 2D on the plane, and we're going to solve for the trajectories. And when we solve for the trajectories, we have n equals, and we have some choices here. 1, 2, 3, 4, none of above. No talking. Do it yourself. I'll get the clicker working in a minute. I hope. This is a no notes quiz. This is a do it yourself without looking it up quiz. Okay, 15 seconds more. Five, 4, 3, 2, 1. Blast off. Okay, here's what you think. Maybe not. Okay, well, never mind. Let's just discuss the solution here. So our basic mechanics for a particle in the plane is a particle like this, which has some force acting on it, like this. And our basic equation is F is equal to ma, which we can rewrite as A is equal to F over m, which we can rewrite as V dot is equal to force divided by m, which we can rewrite as Vx dot Vy dot is equal to Fx Fy as a list divided by m. And that's two equations. But we also have our kinematics equation, which is that the rate of change of position r dot is equal to v, which we can rewrite as rx dot ry dot is equal to vx vy. And this is two equations. And then we get to the advanced math that we learn in classes like this, which is that 2 plus 2 is equal to 4. Any questions about that? Take a picture of that. Tell your parents what you're learning in college. 2 plus 2 equals 4. Any questions about this quiz or about the solution? In case you're wondering how other people did, about half of you said 4, and about a third of you said 2, and then about 5 people each said 1, 3, and none of the above. No questions about this. Okay, so now we'd like to go back to our question, which is how does something move with friction? And we had this self-graphing thing here, where we could graph the trajectories of particles. It's not a perfect thing because I can't get all particles to have the same size or the same velocity. So they have different masses, they have different drag constants, they have different initial velocities. But I get a range of trajectories out of this by looking at the tangent curves. And one set of trajectories is the one that goes like that. And then I've got some other trajectories that are looking something like that. And then I've got some others that are looking something like that. And the question is, what is the shape of these? And remember, the quiz last class was when the drag is very high, what does this shape become in the limit as the drag gets very big? And we want to work that out. So I'm going to work that out now on the computer. And this is going to teach you a little more computer stuff, as well as hopefully some things about how things move in space. Okay. As this is getting set up, think about questions you want to ask about overall logistics of the course or content of the course or anything like that. Questions about anything while the projector is warming up? Not so happy today, seems like. Any problems out there I should know about? It's getting to be prelim season, it's getting tense. Like, why do you guys seem so serious today? You're not serious today. I'm misreading the whole thing. Okay. That's too dark. That's about as good as I can do, I think. Okay, so we're going to try and solve these. We're going to try and get this onto the screen. Good. Okay. You had all that time to think of a question. Anybody think of a question? Yes. What can I tell you about the prelim? It covers through the homework, which is due next Tuesday. The reason we do that is so that you won't feel like the homework is in conflict with studying with the prelim, and the solutions are posted, I think, anyway. It covers anything in lecture and text through roughly today's lecture. Or recitation. It could have MATLAB on it. What didn't I say that you want to know? What? I'll tell you one thing. I'm only so creative. And each time I go to write a prelim, I write it from scratch. But when I look at my old prelims, they look remarkably similar to each other. So I'm not going to try to write this to be like the old ones. But it's a fair bet that I haven't become super creative in the meantime. Okay, I don't guarantee it. I try, but it might be that looking at the old prelims would give you a hint about how things would go. Okay, any other questions? Yes?
Is MATLAB on the prelim? How much of the syntax do you have to know?
I consider it mean grading if a lot of points is taken off because you have a comma instead of a semicolon or a semicolon instead of a comma. On the other hand, if you don't know a lot of the syntax, you don't know anything. So there is this point of view that some people try to take, which is, well, I could always look it up. But you could also say that when you go to France and you don't speak French and you say, well, I could always look it up. You're not functional unless you actually know a bunch of words and a bunch of grammar. So you have to there has to be some sign that you know what the commands are and how to use them, but small errors should not take off a lot of credit. Does that address your question? Yes? It could be a whole question, it could be all three questions, it could be a part of a question, it could be that one or more of the questions could be answered with MATLAB or without MATLAB. It could be any mixture of those things. Yes?
So, question, like, could it like break it down, just like show either like a numerical solution or how you do it?
Well, if you read the covers of my old exams, you should do that. Look up at my exams from last spring. You'll see that it says that for any question of any type, if you can write MATLAB commands, which would give you the right answer, you will get a lot of partial credit, at least. Does that address your question? So whether or not MATLAB is called for, if you can give a coherent answer with MATLAB, it's worth something. Yes? Yes and no. I don't like to give time pressure exams, and so I try to write an exam which a competent person can easily get done in an hour and a half, but I will give you 3 hours to do it. If things are good, by the end of 3 hours, there will only be 3 compulsive people in the room. Okay. And most people will leave maybe a little more than an hour and a half because it changes the pace of the exam, which is that you don't have to rush. So I'll make it so that if you rush, you could easily finish in an hour and a half, but I'll give you 3 hours. Does that address your question? Okay. So we were doing mechanics. Mechanics leads to differential equations. Differential equations are mostly hard to solve with pencil and paper. And even if you solve them with pencil and paper, you have to use a calculator or computer to graph. We've been learning numerical solutions, which we can solve all kinds of differential equations. And now I'm going to go on with numerical solutions for the problem we're doing today. I want to jump immediately to the question that was asked on Piazza about do we have to know the midpoint method. So what I've done here, previously when we started, we wrote one program or one function that did everything. It solved the differential equation, it set the constants, it had the differential equation in it. Then we got this idea that we should put the differential equations on the side someplace and call that the right-hand side function, so that the equations that we're solving and how we solve them are separated. Then what I've done is I've taken the part that used to have Euler's method in it, and then we changed it to midpoint method, and I turned it into a single command. So right here in this program, there used to be a block of code, and to save time over the weekend, I moved it rather than watching you cut and paste it. And what it says, if we give the initial conditions and the parameters and the times we want to know the solution, we want to solve the differential equations using the midpoint method in this case. So now I've isolated out the part of the code that solves the differential equations. So I've got one part of code which is the differential equation, and then this other part which is solving the differential equations. And bit by bit, we're writing our own version of what MATLAB is called ODE 4.5. And to make you understand it, we're writing it ourselves, and you should know how to write it too. The whole idea in Euler's method is all in these 4 lines. So here's the midpoint method, of solving the differential equation, which it goes like this. If I know the current value of the state, z, that's the list of positions and velocities, I know the parameters, and I know the time, the differential equation, which we've called right-hand side, it will be different for different mechanics problems, tells us the rate of change of all the variables. And that's how we predict the future. And I'm now going to call that z.temp. This is what I think for now is how things are going to change in the next increment in time. Now, what I do is I use that rate of change, and I go forward half of a time step. And I calculate a new value of z, and I call that the new temporary value of z. Now, having gone that half time step, I go that half time step in time. I go that half time step in z. I take the parameters and I calculate the derivative again, and then I use that to calculate the new value of z. I take a whole time step. So I provisionally go forward half a step, calculate the rate of change of things, go back to where I was, use that provisional slope, and calculate the whole step. And graphically, I showed you why that should be much more accurate than Euler's method. Euler's method is just these 2 lines, and the first 2 lines here are Euler's method for half of a time step instead of a full time step. So it's like you take Euler's method for a time step, then use that to calculate a derivative, go back to where you were, and take a full time step. It sounds like it's less efficient. Why don't you just march along with Euler's method? But it's actually much more accurate because of that picture that I drew. Yes? I could call this z. I just happen to call it z new temp, so we remember that we're not going to stick with it. So this is taking one Euler step of only h over 2.
Then when you actually calculate z dot, would you calculate it from the original state, not from
No, I calculate z dot at that new place. Having calculated that z dot at that new place, then I take a whole time step back from the old place. And why is that? It's because I'm going from an old place to a brand new place, and I want to get the average derivative, and a good estimate of the average is what it is in the middle. Now, I don't know exactly what it is in the middle because I don't know the exact solution, so I guess where it is at the halfway point using Euler's method, evaluate things there, go back here, use that slope to take a whole step, and if you just draw curves, you see that it comes out very close to where you want to get to, as opposed to 2 Euler steps, which we'll miss by a lot more. Okay, so but if you look at this loop here, it has z in it as just a list of z values, and it has this right-hand side, and the right-hand side is just telling us the rules for z dot. So this whole thing doesn't have any mechanics in it. It just works for any differential equations. And it could work for 2 equations, 3 equations, 5 equations, 50 equations, 100 equations. This is a general purpose solver of differential equations. All of Math 293 right here. Now we want to save the results. We've got this new value of z, then we're going to calculate a new value of z, then a new value of z. The output of this whole thing, we want to be an array of values of all the values of z at all the different times. Now, for no good reason, we choose to think of the list of z values as a column vector. But when we store it up, we store it out as a list of row vectors. Now, why do we do that? It's because that's the way MATLAB does it in ODE 4.5, and I'm just copying that. So it could be we had a series of column vectors for the different times, but instead we think of like in Excel, we work down the times. Each row is a time. So it's a set of rows. Each row is a set of z values. So we're working with z as a column vector. When we store it in this one row of this array, we transpose it and turn it into a row vector. And then we stored it for the ith row, and then we're going to do that row after row after row, and it tells us all the positions, all the velocities at all the different times. That's the output. And then we put as an input here all the times we wanted to get things, and we'll make that also all the times of the outputs. So we get out 2 arrays, a column vector of times, and an array where each row of it is the list of z values. So now going through this whole thing, we solve the differential equation by taking the list of times, the initial values, and the parameters. We temporarily set the new value of z to z0. We look at all of the different times. What's that number? That tells us how many times we're going to have to go through the loop. Here, this n times. That's the number of times we go through this loop. This says nodes, but that's really, you're reading that wrong. That's n-ODEs. That's the number of ordinary differential equations. This is going to work for 2, 3, or 37 differential equations. We'll figure out what the intent is by the size of this vector, the number in the initial condition, the number of variables in the initial condition. For this problem here, it would be 2 plus 2 equals 4, the one that we'll do first in lecture. We'll zero out this array, which is going to be the output. We'll set the first row equal to be the values at the first time. And then we go through this loop, which I just explained, save the rows one at a time, get the final t array, and then we have our output, which is this t array, z array. So here's all of Math 293 in one little block of code. So any questions about that? Yes? Yes, this apostrophe means transpose, and the way this peculiarity, there's no right or wrong to it, it's just a choice we made because we're copying what MATLAB uses, is we're thinking of the state vector as a column vector, but when we store it up for the whole list of them, we store it up as rows of this matrix. So this is turning this column vector into a row vector. Any other questions? Yes?
What exactly does the RHS function do?
So the RHS function, let's just jump to that right now. This is I've set it up for exactly the mechanics problem we did in lecture last time. What it does is it calculates the rate of change of all the variables in terms of the present value of the variables. So it's called RHS for right-hand side. We write z dot equals right-hand side. It's the rate of change of z as calculated from the present values. In mechanics, we know the rate of change of all the positions by knowing the velocities. Those are two of the equations. And if we know all the positions and the velocities in time, we use the laws of mechanics and the material properties to calculate the accelerations, which is the rate of change of velocities. So the right-hand side, in this case, not for all of Math 293, but for all of this case, the right-hand side is the laws of mechanics plus the laws of geometry. So let's just break it apart for this particular problem. We're going to have F equals ma for this problem, and it's all going to be in this little complex place. So this is the laws of mechanics. What's the essence of this whole course, TAM 2030, is to be able to write this block of code. So I want to be able to draw a picture, describe a physical situation to you, and your goal is to be able to write this little block of code for all different problems. That's the core of this course. But now we want to do more than that, which is use this to solve the differential equations and make pictures and so on. Okay. So now let's do this particular problem. We're saying if we know the current state and the parameters and the time, we're going to calculate the rates of change of things. This list of four numbers, we're going to interpret the first two as being the positions and the second two as being the velocities. Now, what are the laws of mechanics and geometry we're going to use to figure out the rate of change of these things? Well, the rate of change of the positions is just the velocities. So this is two differential equations here written in this tidy way. You don't see differential equations here, but I'm going to take these two numbers, I'm going to stick them in here. That's the thing which is called z dot. That's the thing which is used by the crystal ball method, the midpoint method, the solver of the differential equations. So the output, the rate of change of these four numbers, the rate of change of the first two is r dot, which is just velocity. Very simple, almost too simple to look at. The second part, which is F equals ma, is here. So this is F equals ma for this particular problem, the one that we did on the blackboard last time, which is a particle flying through space in 2 dimensions. What was F equals ma? Well, here's acceleration multiplied by mass, but I divided by mass. And I said there's a drag term proportional to the velocity. Remember, the velocity here is two numbers, and it says that the drag force, a list of two numbers, is a constant times the velocity of the particle. And then there was also mg divided by m, so the m cancels out, and there's a downwards acceleration. And why do I put a 0, 1 prime here? This is the x component of the acceleration, and this is the y component of the acceleration as a column vector, because I'm arranging this thing as a column vector. So now this tells me the acceleration. This is, if you say the core of the course, the real core of the course is being able to write that equation. That's F equals ma. That's the whole mechanics in this lecture. And then we say, what's the rate of change of the velocity? It says v dot, and here we have it. This is the differential equation for rate of change of position and velocity using the laws of mechanics. Does that address your question? Okay, you have a question.
So z dot is a column vector?
That's correct.
But at the end we have to switch it to a row vector?
At this point, it's just a column vector. And this program here, which solves the differential equation, treats it as a column vector all the way until it stores it in the result to save to pass back out again.
Can we just treat it as a row vector? Or
You could just treat it as a row vector the whole time, but then you would be learning something that you'd have to unlearn when you use ODE 4.5, which is the MATLAB solver. So this is what somebody brilliant in the math works decided, is that z is a column vector, but when it spits it back to you in the end, it's a list of row vectors. And so I'm just doing it consistent with that. Okay, we could have done row vectors all the way. It would have been a lot cleaner to think about. Yes? Michelle? Right here? This is the initial conditions. So we're solving, the differential equations we're solving are all called initial value problems, where you give the initial positions and velocities, and then we use that plus our knowledge of how the world works to predict the future. That's a column vector. Yes? in the differential equation, what is this part right here? So this is, remember, part of the differential equation was minus mgj. That was the force on the object from gravity was minus mg times the unit vector in the j direction. When we break into components, the y component is minus mg. This thing we're calling velocity and acceleration has two components, x and y component. The second component is the y, the first is the x. So this whole thing says minus g. Right, if I wanted to write that in a more readable way, it's just I don't have the variables there. This is what I have here: minus m times g divided by m. It's the force due to gravity, which is only in the y direction, divided by the mass. Okay? Does that address your question? Yes? Yes. The reason I chose linear drag was so that I could show you the beginnings of an analytic solution at the end of lecture last time, so you could compare, in principle, an analytic with a numerical solution. By this quadratic drag, you can't solve it with pencil and paper. Nor can I, anybody I've ever met, nor can Gauss. But it happens that Gauss, remember Gauss is a famous name in mathematics, spent decades of his life doing numerical solution of exactly this equation with quadratic drag. Why is that? Because in the olden days, like the present days, the big funding for science was how to kill people better. And they wanted to know how cannonballs fly, and he spent lots of time calculating how cannonballs fly using these equations, which pretty accurately calculate how cannonballs fly. Yes? I'm putting in two vectors. This list of two numbers, and then on the next below it, another list of two numbers. So altogether, this is a list of four numbers arranged as a column vector. Say again? V dot, yes. This is two numbers here. Right, so this is two numbers multiplied by a scalar, divided by a scalar. So this is still just two numbers in a column vector. And this is two numbers in a column vector. And they're added together, gives two numbers in a column vector, which goes here, which goes underneath these two numbers, which makes us a list of four numbers. Does that address your question? Any more questions? Yes? Line 70 is just the very first time before we set things up. We want to know what the new temporary value of z new is. And line 75 is storing that into an array. Remember, the output of this thing is an array. But inside this program, we've got all these variables we're keeping track of, one of which is this thing we call z new, which maybe I don't use at all. Here, I use it in this one line of code. Does that address your question? So it's just the z new part is getting ready for this line of code. This is storing the first line of the array. Okay, any other questions? Now, so we've got this block of code, which is all of Math 293. Any questions about why I say that's all of Math 293? And then we've got this line of code, which is all of particle mechanics. All we have to do is change little pieces here and there to do every different particle mechanics problem. And then we've got the stuff on top, which is just setting things up. Clear the variables. Let's decide what time span we're going to solve. Let's put the initial conditions for position and velocity. Let's set the parameters that we're going to use in the problem. Let's set the initial conditions that we're going to pass into our solver. And then once we've got the solver, let's unpack the array, all those z values back into x values and y values, and then let's plot some things. We've got 3 parts, just general bookkeeping, setting up the problem, and then the differential equation and the solution. Okay, now I've set up this trajectory problem. I've set it up for, let's see, what parameters did I pick? I put gravity equals 1. I just put all the constants equal to 1 to start with. This spring constant isn't even used in this calculation. That's just in case I want to go on with this lecture and do other problems. But I've got a mass, a gravity, a drag constant, which for now is 0. I've got other masses in case I want to do a problem with 2 masses in it. So I'm not using that for now. And I've got my differential equation. Now, let's see, what am I starting with? I'm starting with initial position of 0s, and I'm going to launch something at 45 degrees with speed of 1. And I'm starting out with no viscous drag, and I run this thing and see what I get for a plot. Where's figure 1? Figure 1. Okay, so what do I get? The thing goes up, and it comes down. And it looks like your ideal freshman physics, high school physics, parabolic trajectory. What if I run it for a little longer time? It does what? Let's see. Did it run for a longer time? T1 equals 3. It should have run for a longer time. Run for a longer time. Say again? I'm stuck in the debugger. Thanks. DB quit. Go back and run this thing again, or make it disappear by accident. This was trajectory. Oh, I docked the window by accident. Undock it. Run it again. Okay, I run it for 3 seconds. It goes up and goes under the ground and starts penetrating into the center of the Earth. Okay. Now, if I run this, if I launch it faster, then I run it for that amount of time, and it'll go up. Okay, so here's our sort of parabolic trajectories. Any questions about that? What if I don't do such an accurate integration, but I instead integrate for, say, a big time interval? Then I don't get such an accurate solution, but it's still pretty good. Theoretically, it should come right back down to the ground. Let's see. Let's take an even worse one, like a time step of 1. That should be really bad. It's really bad. Okay, so that was not a good solution. 0.5. How does it work out? Still works out pretty good. Now, why does it work out so accurately when it's just an approximate method? Is that this is a quadratic method, and it turns out it's exact to second order. This is a problem whose solution is just a parabola, so it comes out, it gives exact solutions. Now, if we add some drag to it, that's no longer just a parabola, there's exponentials. Remember on the blackboard last time, exponentials. What do the solutions look like? Here we get a solution. See where it ends up here? Now when we do it more accurately, say take 1/10 the time step and run this thing, it just changes the solution a little bit. Now what happens when I add more drag to this? What happens to the shape of the trajectory? So instead of 1, I put 4 here. What happens if I put 40 here? Much more drag. It goes crazy. Now why does it go crazy? Is that a nature of the solution, the real solution, or is that a numerical artifact? How do we check that? Let's just go back and look at the first few time steps, like 0.2, and see what it does. It doesn't even quite start at 0. Who knows what's going on here? So let's just take a finer time step, see how it looks. Ah, that's more like it. And now let's go back to our longer period of time, 2. Run this thing. Look what the shape of the trajectory is. It goes up, comes down. So I don't know if you remember, but it's a famous so-called science misconception, is that people, before they learn mechanics, they think you throw things up and then it comes down. Then they teach you physics to show you that things really go in parabolic trajectories. And who is right? Well, if there's a lot of air friction, the naive people who didn't take mechanics are closer to the truth. The cartoon physics is closer to what happens when there's a lot of air friction. It goes up very fast, slows down, then gravity kicks in and it falls straight down. So there's this little curved part up here, but basically you get this triangular trajectory, which a few of you got right in last class. Now, does this answer depend on it being linear drag or quadratic drag? With linear drag, you can solve this all in terms of exponential functions. It doesn't look like exponential functions here, but it turns out with the x and y together, this solution just comes from exponentials. And with the quadratic drag, even if you're Gauss, you have to solve it numerically, but you still get this triangle trajectory. Okay, any questions about this problem? Yes? Can I do it with quadratic drag? So do you want to? Yes, I will. If you want to see that. So we want to do this problem with quadratic drag. It means we've got to put a v squared here. But v squared, remember, there's a sign problem. What do we mean by v squared? So what do we mean is v times the absolute value of v. So I could v times the norm of v. And now I've got a v squared quadratic drag. It's that simple. Okay, now just so things don't mess up, let's just go back to zero drag or very small drag and see how things look. Parabola, now I'll put in a little more drag. 1, run this. It starts to look more like our triangle wave. 10 drag. Starts to look a little more like that. Now, here's the funny thing about this. If I put more and more drag in here, this one, this beginning part just gets to be so teeny. So if I want to start to see what's going on, I've got to launch it a little faster. Now it's done it's gone unstable somehow, so I've got to integrate it for more time. I mean, with a finer resolution, and I start to see this triangle shape coming back again. Does it address your question? Okay, so we see this triangle shape coming back. And yeah, so there's quadratic drag. What if we don't want to do quadratic drag? All of a sudden, we're not interested in killing people and how cannonballs move. We're interested in how the moon goes around the Earth, or the Earth goes around the sun, or something like that. So we want to do some problem involving motion of a particle around a planet, something like that. So we want to change our differential equation to being one that doesn't have to do with this drag, but has to do with gravity. Okay, so how does gravity work? What are the differential equations? Well, because I'm sitting here at the computer and I don't want to get up, I'm going to draw the free body diagram in my head. But what is the differential equation for gravity? Is we have a gravity force which is in the negative r direction. In fact, it's r divided by the magnitude of r. And that's the direction of the gravity force. It's towards the center, and that's a unit vector in the right direction. But I want to get the magnitude right, and for gravity around the Earth, something like that, it goes as 1 over the radius squared. So I put 1 divided by the radius squared. What's the radius? It's the norm of r. That's the fancy math word for the magnitude of r. And then I'm going to square it. There are other ways to write this. And then I multiply by that unit vector. Now I could combine terms here. I have the norm of r squared, the norm of r, and have r over r cubed. The vector r divided by the magnitude of r cubed. But here it is just in a nice, tidy way. And now I haven't put in gravity constants and stuff like that. Let's just say all the constants are 1, because we're just trying to understand the differential equations. So now this is assuming that all the constants are 1. This is a motion of the sun, the Earth around the sun, the moon around the Earth, the satellite around the Earth, and so on. Let's give it some decent initial conditions. Let's see. We don't want to start it right in the middle, because that's singular. The forces are infinite. So let's start it out here let's say on the x-axis, and let's start it going in the y direction. So we're launching it roughly with the intent maybe of it going in circles if we've got the magnitudes right. Okay, any questions before I draw the plot? Do you understand this initial condition? Starting on the x-axis, throwing it in the y direction. And my differential equations, and this is the gravity differential equations, is I've got an inverse square law, meaning I've got a force proportional to 1 over the radius squared in the minus r direction. That's the unit vector in the minus r direction. Clear? Not clear? Okay, so what are we going to get for this motion? It starts out kind of nice. Looks like I might have got my circle. So I want to run this for a longer time. Maybe I don't need it to be so accurate to start with. And a nice amount of time for problems like this sometimes is 2 pi. And see what I get. Very nice thing, right? Now, what if I didn't integrate so accurately? Would I get such a beautiful circle? Not really. So if I, 0.5, not so accurate, 0.3 here, it gets to be more like a circle, 0.1, more and more accurate. And by the time I got out to 0.01, you couldn't see the difference. If we really wanted to see the difference, maybe if we go 20 revolutions, 20 orbits, we can start to see it blurs a little bit. See that line got a little fat. Okay, let's go 100 orbits around. 100 orbits. It's thinking about things. It's thinking. It's thinking too hard. Now, why is it thinking so hard? Is because I've got a print line there that's slowing it down. Where was that print line? It kept printing out R, so it's down in some loop. I had some R. Did anybody know where that was? Right. 58, comma. Okay. So now it should run a little faster. Wishful thinking. Now what's the printing out? Z dot temp. Z dot temp. Okay, now try it. Came out pretty good. Okay. What if we launch this at a different speed? What will happen to this shape? This is one of the most famous results in all of science, is the shape that comes out here. If I put a different speed here, that shape is going to be what? An ellipse. Launch this thing. What? 1.5 is a big number, right? There's 1.2. I didn't do a very long time there. Do it for a little longer time. A little longer time. Okay, very good. 1.5. Was 1.5 just too big for this thing? Escape velocity. It's gone too fast. What's the shape of this curve, by the way? That's a hyperbola. If I get just the right shape, just the right launch speed, I'll get a parabola. If I put in a small speed here, I'll get a different ellipse. So if I put 0.5 here, I get a different ellipse. Now that should be an ellipse, but I'm not integrating accurately enough. If you get a solution like that, is that a real solution or is that from integration accuracy? You can't know unless you up the accuracy and see if it starts to converge to something more like an ellipse. Okay. Here we've got this thing for one particle, and I can put any force law I want on this. I could have added viscous drag to this. I could have added quadratic drag. I could have done a spring. What if I want to know about a mass on a spring? Let's just do that as one more case here. So I've done this gravity case. So I'm going to do a mass on a spring. V dot is equal to, and then I'm going to say it's minus k, and this is minus p dot k. Is there some mistake that somebody's, what? What's the problem? Not a problem. Okay, so I have a spring constant. The spring is going to be pulling in some direction. What's the direction it pulls? It pulls in the direction of a unit vector towards the center. So it's just exactly that same term there. And then how hard does it pull? It pulls with the spring constant times the increase in length. What's the increase in length? It's the radius, which is norm of r, minus the rest length, which was p dot L0. And then I close this, and then I've got to make sure I've passed in a p dot L0 up here, and I haven't. So I'll put a p dot L0 equals 1, my favorite number. And then I run this thing and see how this works as a spring problem. And somehow I've done that bad thing of forgetting to put a semicolon someplace. Right there. Okay, so here's a mass on a spring flying around. And I can, you say, is that weird shape a numerical error, or is that really the right shape? How can I find that out? I change the numerical step size and see if it changes substantially. And I run it again, and it does not. That's really the shape. There's no reason to think I should be getting nice closed orbits out of this. I can run it for a longer time, and I get craziness out of it. And what is this? Well, it's hovering around this radius of 1, which was the rest length, and it's oscillating back and forth as it goes around in these circles. If I want to make it look more beautiful than that, I could stretch the spring more to start with, and then run it, and then I get almost closed orbits, it looks like, but that's just a matter of luck. It won't work out like that if I just change some number a little bit. Okay, any questions about this whole solution? So I'm sure some of you are sitting there bored, but the thing is, it's a beautiful thing. We've got this set up, and we can now draw all kinds of graphs, any motion of a particle with this numerical solution. One question, then we'll end. Yes? You're just stretching? Okay. Yes? I've been pretty good about posting things, and I will continue to try to do that. Yes? Say again? How do I know if it's right? There's various checks. Why don't you ask that question next lecture, and we'll talk about the various checks.